Up with 22. Maybe I can make equals. Nope, let's put that one. By the way, if you would like your extra practice 123 you turned in yesterday back, stop by after class and I can give it a quick look and grade it. With a chance
Just separate with the space.
No, I know how to do it.
It's too big. The point of it, unless it's degree of thick.
It's gonna go with
I know that you do like the reproduction stuff. Some of every
Yes. Are you interviewing alumni at the school? Tell us.
No, it's kind of like a competition.
Oh, there. Oh, cool. Let's see. This is right. So I'll try to get it.
Yeah, I was getting the note.
Ready?
I said two, and then I was like,
Discuss it.
no, I know, but
This one goes up to.
Okay, here we go. All right, are you ready? Okay, so if you know for a fact it's geometric, you don't have to show the divergence theorem. And if you're just in a habit, you just check the divergence theorem first, and that's cool. While I'm thinking about it, though, I can't remember what homework it was, but I had people not quite clear on geometric or not. This, geometric, yes or no? Yes. This, geometric, yes or no?
Yes.
Yes. This, geometric, yes or no? Let's see, what was I trying to get to? 4 to the end. Geometric, yes or no?
Yes.
Yes. This, geometric, yes or no?
No.
No. No, not geometric. Okay? If there's a single n in there that's not exponential, it's not geometric. Watch, assuming it starts at 1. It's 1 over 3 to the first, plus 2 over 9, plus 3 over 27. Now you tell me, is there a single factor you are multiplying by to get from here to there every time? No, there's way more going on than that. It is not geometric, not. And you cannot use the formula. You can say it might converge by the divergence theorem, but that's all you're going to do. You're done. That's the most you can do right now. You couldn't go any more.
for that last one?
It's not geometric. Yep. You could say the best you could do at this stage in your education is to say the terms do go to 0, so it might converge. But as far as proving convergence beyond that, you're not there yet. Okay? It's not geometric. All right. This then is geometric. You cannot, when you have a sum or a difference, you can't treat it like it's one geometric. You must split it into 2. 2 over 3 to the n. So, it is geometric, but in this case the common ratio is 4/3. That is not less than 1 or greater than 1 is also fine. So it diverges. and you're done. Okay, the fact that this converges just means it's infinitely large plus something finite. Well, great. What does that sound like? Still infinitely large, right? Are you with me? Okay, cool. Let's talk the old lesson of the day. This one is so cool. It's just one of those mind-blowing lessons. Love it. Improper integrals, parts 1 of 2. There are 2 parts to this. This is part 1. You were taught to find the area of a bounded region from, say, 1 to 3. How do you find the area of a bounded region? Do an integral, okay? However, if you did an unbounded region, instead of going to 3, you went to forever, well then, what's the area of the curve? Could be finite, could be infinite. It depends, just like series. Sometimes it works, sometimes it doesn't. Well, would you get out your calculator, please? And let's investigate. Can you let me know where the ghetto calculators are? Who's got 84? Go get up. You know, they're fancy inspired. Okay, here we go then. That'll make it easier to teach. Would you please put 1 over x, the directions on your paper, but I will also walk you through it. 1 over x, please. Graph 1 over x. And then in order to get the point, we're going to then restrict it to the first quadrant. So would you go to menu, window, and let's start by going from 0 to 10 in x. The scale is up to you. It makes sense to go by ones to me, but it's up to you. For the y, negative 0.2 to 0.5. Shoot. Is a good one. There's your graph. Are you with me so far? Okay then. What's that tab thing going on? What is that? Oh, okay. All right. Now then, we're going to talk area accumulation. So would you go to menu and analyze graph, and I'm going to go, instead of bounded area, I'm just going to go to integral, okay? The lower bound, rather than use the slider, would you just type in 1, enter for the lower bound? Now the upper bound, I want to look at the slider. Look at that area as I go. 1.8, 1.9, 2. It's growing, it's growing. I guess we'll stop at 10-ish, whatever you're close to, and record. At the point 10-ish, the area is about, depending on where you stopped, about 2.271. I'm going to record the area at that point is about 2.271. Again, if your decimal's a little different, that's not a big deal. Don't worry about it. You with me? Okay. Now, I'm about to do it one more time. Or actually, several more times. So, now we're going to increase the tail a little bit. So would you go back to your window, and this time let's change it to 1 or 0 to 100. Leave the y the same. And now we're going to also recalculate the area. So menu, analyze graph, integral. Still start at 1 for the lower bound. If you just type in 1, enter. And then for the slider, look at the area as you go to the right. 3, 4, growing, still growing, still growing. When you get to 100, I'm about in the ballpark of 4.5-ish or so, 4.6-ish. Are you down? Okay. Let's continue on to 1,000. Whoa, that's bad. It does not do that. But you get the idea. Change your window to 1,000. At this point, the tail is going to be very small in y. Let's go with analyze graph, integral from 1 to, and look at the area as you go on down the tail. 6, 6.4, 6.5, 6.6, 6.7, just continues to grow. Okay? Well then, 6.9. It does not seem to be topping out. I continuously grow. Now I could keep doing this process, but I think you'll see that it is not approaching a limit. It seems like as x goes to infinity, the area is growing without bound, I think. Are you with me? All right then. Well, let's pick up the old pencil and think about this in a calculus sense. We're doing area under the curve, so it is logical to set up an integral from 1 up to, well, infinity. We're trying to go forever. Under 1 over x. Now, when we did this process, we were saying what happens as the upper bound goes to infinity. Now let's create or name some upper bound. I'm going to call it a. So I really am saying as I go from 1 up to some point a under the curve, what happens? And I'm especially interested in what happens as a goes to infinity. Well, if a goes to infinity, that implies a limit. What happens to that area as a goes to infinity? Well, after that, it's time for a little calculus. The limit is actually the last operation that's going to happen. We first want to integrate. What's the antiderivative? Central log of the absolute value of x. I'm going to leave off the absolute value because we're talking a positive region here. From 1 to a. Then I apply the fundamental theorem of calculus, which is to say I evaluate at the upper limit minus at the lower limit. Then finally I'm ready to evaluate the limit itself. Natural log of 1 obviously is 0. So as a goes to infinity, the natural log of a goes to infinity, which is to say the region or the area diverges. Now you could say infinity, you could say divergence. Sometimes improper integrals diverge, just like infinite series sometimes diverge, but sometimes they converge. Consider the same principle of 1 up to a point, but this time under 1 over x squared. Would you? I'm just going to restart, if you don't mind, restart my scratch pad, although you don't have to. I'm going to go with 1 divided by x squared. Oops, or not. 1, oops, never mind. 1 divided by x squared, check. From window of 0 to 10, boom. Negative 0.2, 0.5 seems good. Boom. All right. This time, I don't know if you know it because the window's changed so much since I last. But this function decays a lot quicker. 1 over x was around here. 1 over x squared decays really quickly. So let's see what happens if we go from 1 to 10. Boom. 0.897 for, it's a pretty decent. 0.897. Then, now I like the slider. I understand I could probably just calculate these calculations, but I like to look at the numbers as they grow. Maybe it's just because this technology is amazing to me. 1 to this time. Now, I didn't change my window, dummy. Not bad. Change my window to 0 to 100. I do. Just because I guess you could go straight to 1,000, couldn't you? Seems like it's not as suspenseful. But okay. All right. I like the suspense myself, but whatever. 6. Okay. Now, I'm going to 1,000 now. Watch what the area does. .996, .997, .997, .998. Oh, it's going smaller and smaller and smaller. It seems like it has an upper bound. Seems like it's approaching 1. Okay? You get the idea? Approaching 1, question. Now, let's see. Calculus wise, the question now is, if I want to integrate from 1 to a, what happens as a goes to infinity? The antiderivative is the first thing to happen. Negative 1 over x from 1 to a. The evaluation is the next thing to happen. That's negative 1 over a plus 1 over 1. Do you agree? As a goes to infinity, 1 over a goes to 0. And so we actually converge. Now, this to me is mind-blowing. Say I threw a pi in front of that. What would the answer come out to be? Pi. Okay, now why would I do that? Well, to me then, that says that this area under the curve is infinite. Infinite. Darn, just stole away my thunder. Infinite, okay? Are you with me? But if you take that infinite area and revolve it around the x-axis, the volume is finite. That's cool, man. Okay? Infinite area, yet finite volume. In other words, you could fill it, but you couldn't paint it. Okay? That's, to me, is cool. Yeah. That is awesome. All right, now, it's always the case, okay, and this, I understand this, Mr. McKellips has got physics to worry about, okay, but in math class, okay, you will never say the limit from 1 to infinity and then actually integrate. You will never do that. You will never do that, because to me, it feels like you're saying, well, if I integrate from 1 to love, it's negative 1 over x from 1 to love, and that's negative 1 over love, plus 1 over... What does that mean? That means nothing. Nothing. Okay? That is not acceptable in math class. All right, just like he's got other fish to fry, and if he does that, I don't want to know. I don't want to know you do it. I don't. It's like if you went out, whatever, smoking crack on the weekend. I don't want to know. Actually, I want to know, and I want to stop. But with this, I don't want to know. All right. You don't do that.
Everybody's doing that now.
No, not enough. This is a little haven of beautiful math. No, never. Okay? If you hate me, then by all means, when I die, rather than spit on my grave, throw one of those babies on my grave. It'll be way worse. Each of these then is the idea. Each one, I know it feels like redundancy, but each one has a purpose. So would you do each of these for us? Fundamental thermal calculus. That makes me a little sad that you don't.
I don't appreciate.
Oh, okay. So fundamental thermal calculus means.
If we get shirts, we're definitely going to put that on.
Yeah.
One to the limit of
I don't give me one.
You wrote.
They come now. You don't. The problem is that that's the way the problem is, that you don't continue on with that. Okay. That's how they express. They don't write the limit for you in the problem. It'll come that way, and you then take it to proper method. Okay?
Look, you can have the interval from 1 to infinity of a triangle. It's gets you.
We'll go over these in just a second. Okay, so which one has a different surface?
I hate this.
I wrote way too bad.
I like you just trust me on that. You're like, look, got it. Therefore, it's right. That's a terrible strategy. Well, I mean, if that's still
By the way, A is arbitrary. It's not universal by any stretch. You can use whatever letter you want. It doesn't have to be A. Yeah, sure. Use a whatever emoji.
What if there was a symbol that kind of looks like the infinity symbol,
Yeah.
but it has a zero? What if the size of the
Like lowercase o's, except just edited running, so they're really close to each other.
No, a million times no. What'd you get for the first one?
That's like this is like. And then what explains?
You don't need to make A negative. Just let A go to negative infinity and it's all good.
Oh, wait, is there any? Wait, why did you get rid of the negative one?
It's, I think I lost in it one, it's still there. Or I forgot it, maybe.
He gets excited about something.
That -2 denominator, are you going to pull it out front of the limit, which you can do, or just leave it in?
I pulled it out.
You pulled it out front? That you can do. So that's then 1/4 squared. So what'd you get for B, or the second one, whatever it is? It is -1/2.
I don't know. Maybe the explanation. Well, actually, if you give some, I think I would put yeah, no, so I'll probably just go to like all the two that again. What was that for? Bio. I think that it's like a waste.
Now if you go over and something else fails, and then just go forward.
C? This is the 10. 1/10 power is the same as the 10th root, okay? And yet the 10th root of something infinite still is infinite, so this diverges. You can say it's infinite or divergence, both are fine. Well, the next one's slightly, and pretty darn close. They're both really close to x to the first. X to the, I suppose negative first, sorry.
Are there special ones, or like,
There's one that's the great dividing line, which we'll talk about in 1 minute.
are you the one that called it that, or good?
Oh, no, that's zero. No, nobody calls it.
Are you kidding?
Conceptually, it makes sense, I guess. X to the negative 1/10. So, x to the negative 1/10 x to the negative 10. Negative 10 out front, limit is a equals to infinity. Oh, 1 over 10th root of a, so 10th root of 1. So what about that last one? It is 10.
10. Wow.
10 times 0 minus 1. 10. Okay. Now then, give me a second to digest. Are we ready to move? Okay. Okay. Now notice. Notice here when you have an infinite limit or an improper integral of 1 over x to a power, like that. If p is less than 1 or equal to 1, then the integral will diverge. Now that actually makes a good deal of sense because when you integrate it, it goes up in power by 1, and if it goes up in power by 1, it's either natural log or x in the numerator, and you're going to get an infinite result. If p is less than, or sorry, greater than 1, then even when you integrate it, you're still going to be in the denominator, and as you get infinitely large, it will still converge. So 1 is the great divider. Greater than 1 down there, it'll converge, but less than 1, it'll diverge. Consider, yes, question.
Could we use that logic to say if something diverges or not, like on homework or something?
On a multiple choice question, I'm fine with that. In fact, I encourage it because it saves time, but on the homework, no. Okay. Consider a related question. Actually, is anybody in AP Stat? Just for the benefit, remember in AP Stat, you guys learned about the normal distribution? Which, maybe? No, of course you do. The normal, you don't remember the normal distribution? Oh, sorry. In Algebra 3 honors? Algebra 3 honors?
Yes.
Okay, sorry. You learned about the normal distribution, yes?
Yes.
Sigma is the standard deviation. Yeah. Okay, that's the lowercase. This is a normal, this is the proper integral. You have infinite area on both sides, and yet it does converge. It's called the Gaussian distribution. Yeah, all those tables you used, you know, when you said, hey, what's the percent of the population in here?
Oh, yeah.
That's an integral.
No, I remember being.
Those come from integrals. 34% in here, 68% within one steady.
No, I remember them explaining like how we
So that table that you used with the calculator, those are integral values.
Some of those only for bulk.
That is the normal distribution, yes, that's true. Okay,
No, but like, you just mean like, what if they're like, if it isn't like grounded, it's at the all, if it isn't like,
it can still be skewed if that's what you mean, that,
oh, no, I was talking about like,
like that.
does that have to be differentiable at every point that we occur?
It has to be interval.
It's, okay, so they can have like points.
Yes. Yeah. Okay. So here we go. M and R first start back to back at the 0 on the number line. They walk away from each other. What is the average of their positions as time goes to infinity?
That word process.
Starting at the number line, they walk in opposite directions. What's the average?
Are we assuming that your daughters have
They walk
the
in the
You
same.
tell me.
If they're not
What's
walking.
their average position?
one, 0.
Oh, that's pretty good. You're actually, so what,
I just,
0 makes sense, but that would have to be assuming they are walking at the same speed rate. So you do not know what rates, yeah? Now, consider that question as we look at this question. If I look at the area under the curve, y equals x, from negative infinity, so I'm going this way, accumulating area, to positive infinity, accumulating area this way. That total integral is? Cannot be determined. Divergent. Divergent. Okay, so I have something going to a negative infinity on this side. Let me call it A. But this is something totally different. I'll have to call it B, or I could call them Emma and Harper, if you like, whatever. Okay, A and B is fine. If you wanted to rework this, then it would be the limit as E goes to negative infinity from E up to 0. Now, 0 actually is arbitrary. I don't even know. I don't even have to stop at 0. I could go from E to -2, and from -2 to. That's 0 makes sense, and look, people wanted to have to be 0, but it doesn't have to be 0. Okay? X dx. But the limit is different for the other one. It's a totally different variable doing its thing. H goes to positive infinity from 0 to h of x dx. Now, the antiderivative is the next step in the old process. So 1/2 x squared from e to 0 plus 1/2 x squared from 0 to h. The limit as e goes to negative infinity of 0 minus 1 over 2 1/2 e squared, plus the limit as h goes to infinity of 1/2 h squared minus 0. All right, then here's where it looks like something we've done before, but maybe not. What does this approach as e goes to negative infinity? Negative infinity. What does this approach as h goes to positive infinity? Infinity. Now, is this an indeterminate form like when we do the limit of something and we get infinity minus infinity? Is it like that? Okay. Now, I remind you, back in set 91 rather, you took the limit of a difference, and sometimes you get infinity minus infinity. That's an indeterminate form, and what was your job? You make it a quotient, and you take the limit, and sometimes you can get a limit. Now, is this the same? It's not the same. It's not the same because these are not the same limit. This is not one single limit of one single variable. These are two different limits, two different variables. You can't put them together. There's nowhere to go from here. You can't make it a quotient. Dead end, divergence. Okay? So this is diverging. You have no idea because really it's about how fast do they accumulate. Very good. negatively and positively, I don't know. You with me? Okay. There was a lot one I wanted to get in there that I screwed up last year. I caused a couple of people to going through. Yes. Diverge means fails to convert. Doesn't mean it's infinite. It just means fails to convert.
We should do what instead of
You don't know what.
Yes, and then
one.
No, diverging means you don't know what it converges to, which is true. Okay, Henry.
17. One. Okay.
7? 45? Cool. Okay. Alrighty then, here we go.
Wait, hold on. Wait, okay, no, it's just the domain that I don't understand. Like, I don't know. I thought at my house, that the domain was super fucking.
Okay.
It's just, it's almost weird. Like, the thing where it looks like we're
What did they said integers?
Yeah, they, well, no, they said like t is less than -2 or greater than 2, but then t does not equal 2n plus 1 times pi over 4, where n is an element of 2. Oh, I think
That's a good one.
it's the math. It's the,
Yeah.
that's the answer.
Yeah.
It's the secret that causes you to have to say integers, because that's one of our causes. Well, like, I don't even understand where the 2 was meant as what.
Okay, that's,
It's coming from where the seat is. So you just see like the law.
oh, this is just that, right?
Yeah.
What is this, 6 secant squared,
Where,
2t?
yeah.
And this is maybe 2t over 2t squared minus 4, yeah?
Yeah.
Okay, the domain for this, and you are trying to, okay, just real quick, there are 3 restrictions on domain. Negative in a root, 0 in a denominator, or log of 0 or negative, okay? In the Great World of Math, there are 3 restrictions on domain.
Yeah, only 3.
Only 3, okay? In this case, tangent really has a possibility of taking on that second one. It has zeros in the denominator when cosine is 0. Tangent is undefined if cosine is 0 at any point. I think you'll agree. Yeah? Okay, well, cosine is 0 at any multiple of pi over 2. Pi over 2, any odd multiple, excuse me. Do you agree it's no good at pi over 2, 3 pi over 2, 5 pi over 2, and so on. So, you would, in terms of domain, now this is done in other textbooks. You guys should have learned this in C calculus, but our textbook doesn't do it. You would typically say then that 2t, let's say 2t cannot be not odd pi over 2 multiples, okay? Let's take that as saying 2t cannot be any, how do you make odds? Formulaically, based on n being a whole number. 2n makes even, plus 1 makes odd, right? Are you with me? So n cannot be the, or t rather, sorry, I'm solving for t. If I say what can t not be, t cannot be any 2 plus 1 pi over 4 for n integers as an integer. Okay, n is whole number integer kind of things. You with me? Okay, if n is 1, then I get 3 pi over 4, I'm in trouble. Because 2 times 3 pi over 2 would be 3 pi over 2. You with me? Okay. For the t squared minus 4, I imagine that's a little more old school, so you're probably good there. Do you agree that the t squared minus 4 is positive on the outsides but negative on the inside. Where t is small, I'd square root it negative. And so I'd be cool out here, but not in here. You would typically say then, rather than write it as a disjunction, which you could say t is less than or equal to negative 2 and t is greater than or equal to positive 2, but it's more common to use absolute value and say the absolute value of t needs to be beyond 2. And that says the same thing. You with me? Now I have equal to there from this, but when you go to the derivative, what's different?
Yeah, but it,
Yeah, now we're in the denominator, and those zeros are not good anymore. So we actually need to take out the equal to. Oh, does it say it has equal to? Does it say, and it says the domain of the derivative? Yeah, that's a mistake.
okay.
It should be t is greater than 2, absolute value of t is greater than 2, but I guess you could say t is not any multiple, we already talked about this for any integer. That was a weird answer. See what that was. Does that make sense? Okay. All right. Number one. Number one is, so the problem might be your trig sub, I assume.
Well, how do you, I guess like graph.
Okay, so this is, okay, the thought process behind the graph, once you see it, you start to get a feel for the thought process, it goes pretty easy. Wouldn't you agree that when you have a fraction, you sometimes worry about a vertical aspect?
Yeah.
But that would happen if the denominator is 0. Can the denominator be 0? It can't be 0 in this case, okay? So that tells me there's no break in the graph, it's continuous. The next thing my mind would go to is, as x gets large, y would go to 0, so I know it's going to do that. And it's going to be the same on the negative side, it is an even function. The next thing I'd think was, well, what about the top? As x gets, what's the bigger x gets, the smaller y gets, but by the same token, the smaller x gets, the bigger y gets. So wouldn't y be at its greatest when x squared is at its very least?
Yeah.
What's the least x squared can be? 0. So the most y could be then is 1 over root 10. That's the maximum, which, 3-ish or whatever. It's like that. You follow? After that, they said graph from 2 to 5 and revolve it around the x-axis. Shells, washers, or discs? Disk. It has no hole, it's solid, it abuts the axis of revolution. So it's a solid disk, the volume of which then is pi r squared times height. The height is the next thing I think is the height dx or dy. Dx, and the r is just the function, which thankfully is squared. It's from 2 to 5 by definition of the question. So we get pi 2 to 5 of 1 over x squared plus 10. You could trig sub that. You could do the adapted arctangent thing, whatever you want to do. How do you want to proceed from there? Arctangent, okay. I typically would try and make this 1, so I would factor out a 10 and call this 1 over x squared over 10 plus 1. It's been a while. We've gone mostly our trig sub from here, but is this looking familiar?
Yeah.
Okay. I would then say x squared over 10 is my u squared, which means x over root 10 is my u, and therefore du is 1 over root 10 dx. Do you see where I'm coming from? Okay. That would then mean that, so now I want to, do I really want to use sub, or can I just kind of, do you mind if I just throw in the root 10 here and balance with the root 10 there so I don't actually have to use sub? Are you cool with that?
Yeah.
Okay, because it's a definite integral, I'd rather avoid that if I can. Now then, when I go to integrate this, it's root 10 pi over 10. The antiderivative is arctangent of u. What's u again? X over root 10 from 2 to 5. This root 10 actually went away as part of the du. Yeah. So, I don't know, shall I continue or are we good? Arctangent of 5 over root 10. I think they rationalized in their answer, which I don't care about. If they rationalized, fine, it might be something like, what, root 10 over 2? Okay. If you rationalize it, it's fine. If you don't, that's fine. If you left it like that, that's fine. Okay. Okay. 10. Is 10 still a question? Oh. 10 is a problem. Okay, so did you trig sum, my young pupils? Did you use tangent? Did you eventually then get to 1 over secant squared, which is cosine squared? 3? Which by identity is 1/2 1 plus cosine of 2 theta. We? Okay, so that's 1/2 theta plus 1/2 sine of 2 theta. Now this is where we can't sub with sine of 2 theta. We have identities of trig for theta. So we use an identity. Oh wait, remember that? Use an identity for sine of 2 theta. We call it 2 sine theta cosine.
You know that sign of that? Yeah, that's all.
I'll be right today.
Yeah, did you go it? Hi. How are you doing, my young friend?
Hey, on this. Yeah, I'm gonna redraw it. Well, it's kind of.
They wouldn't be out of control. All right.
That actually makes sense.